Hello and welcome back, everyone. Today we'll be getting into section 11.4, nonlinear inequalities in one variable. Now the basic idea here is we are going to use what's called the let line, pretend temporarily that we have an equation, solve the equation. That's going to give us some critical numbers that will let us cut up the number line into sections, and then we simply test each section in the original inequality. So we'll start with one that is pretty fast and painless. So we're going to solve the inequality x minus 2 by x plus 4 is strictly greater than 0. So we start with our let line. We pretend that they asked us to solve an equation. So whatever the original inequality symbol is, replace it temporarily with a 0. So this is a quadratic. It's already factored. It's already set to 0. So we just solve those two linear equations. So x is 2 or x is negative 4. Those are the two critical numbers that are going to have us cutting up the real number line. Make sure you have the lower number on the left, of course. Occasionally, I do see students rushing and having them switched around. So as you can see, these two cuts, these two critical numbers have broken the number line into 3 sections. All we need is a guinea pig, a little test subject from each section. So I need anything to the left of negative 4. So I'll pick maybe negative 10. You might have picked negative 5. Your neighbor might have picked negative 53 trillion. As long as we're on the same section, that's okay. In the middle, I'll just pick a 0. That's between the negative 4 and the positive 2. Again, you might have picked out a 1. Someone else might have picked out negative 3.1415. As long as it's one thing on this interval and then something to the right of 2 on the number line. I don't know, we'll just do 4. So when we test them out, we always plug them into the original inequality. If they work, shade that section. If they don't work, don't shade the section. Okay, so negative 10 minus 2 times negative 10 plus 4. And we want to know, is that greater than 0? Well, we have a negative times a negative, possibly greater than 0. Negative times a negative is a positive. Positive greater than 0 is always going to be true. It happens this time that the number would have been negative 12 times negative 6, so positive 72. But positive anything would have been true. Since it's true, we'll shade that section of the graph. Arrow on the end, since we keep going forever to the left. We'll talk endpoints in a moment. Trying out the 0, 0 minus 2 times 0 plus 4, possibly greater than 0. So we have a negative times a positive, possibly greater than 0. Negative times a positive is a negative. This time it happens to be negative 8. Negative something greater than 0 is false. So we don't want that section of the graph, so I just won't shade it. And finally, we finish it out with the 4. So 4 minus 2 by 4 plus 4. And we want to know, is that greater than 0? So positive times a positive greater than 0. Positive greater than 0 is true. This time it happens to be, let's see, 2 by 8, 16 greater than 0 is true. If it's a multiplication and division problem compared to 0, we can just use a sign number argument. If it's adding or subtracting or comparing to something other than 0, we'd actually need the numbers themselves. Okay, so same deal. We shade that side, arrow because we keep going. As far as endpoints, I'm not allowed to use the endpoints. If I plug in a -4, I get a 0 for that factor, and 0 is not greater than itself. To tell the reader that, I use a parenthesis, and we just lean the parenthesis towards whichever way we shaded. So same thing on the 2, 0 is not greater than itself. So as far as a graph, that's what our graph looks like. They will also likely ask us for an interval. This one has 2 sections, so we'll need a union symbol. So left bound first. So we approach -infinity, and we keep using all of these solutions up to, but not including, the -4. So again, a parenthesis just like the graph had. Then we'll union that up with 2 approaching positive infinity. Make sure you have that union symbol in the middle of them if it's a 2-part interval. Okay, so the next one, a little bit more legwork to it, but not much. X squared minus 6x less than or equal to 0. So we'll start with our let line. Let x squared minus 6x temporarily equal 0. Quadratic, that one we can solve by factoring. So either x is 0 or x minus 6 is 0. That one's already solved. Add 6 to both sides of the other guy. X is 6. So 0 or 6, those are the 2 cuts we're making in our number line. And here, let's see if I can kind of squeeze it in here. Okay, so 0 is on the left, 6 is on the right, and 1 test point per interval. So maybe a -1, a 1, and a 10. Just one thing per interval. So trying out the -1, -1 quantity squared minus 6 times -1, and we want to know, is that less than or equal to 0? Negative times a negative is a positive. Yes, we do need the parentheses there. So +1 plus 7, possibly less than or equal to 0. 8 less than or equal to 0, that one doesn't make sense. So we will not shade that section. Try out the 1, 1 squared minus 6 times 1, possibly less than or equal to 0. So we have 1 minus 6, possibly less than or equal to 0. -5 less than or equal to 0 is true. Negative is always less than or equal to 0. So we want the stuff in the middle. And then we'll try out the 10. So 10 squared minus 6 by 10, possibly less than or equal to 0. So we have 100 minus 60, possibly less than or equal to 0. 40 less than or equal to 0 is, of course, false. So this time I just want the middle section. Plugging in a 0, I do get a true statement. 0 minus 0 is worth 0. 0 is less than or equal to 0. That's true. To tell the reader we are allowed to use that, we have a nice square bracket involved. Same thing on the 6. 36 minus 36 is 0. 0 is less than or equal to itself. So brackets instead of parentheses, and lean them in on whichever side you shaded. So there's our graph, if they want the graph. And if they want the interval, this time we only have one interval. So from 0 to 6, we're telling the reader that we are allowed to use the endpoints by putting those brackets down. And we can't even go higher than the quadratics. I might do x minus 2 by x plus 1 by x minus 5. And we'll say that's less than or equal to 0. So this one is a cubic, not a quadratic. But since we are in the factored form when we set up our temporary equation, we already have it set up where we have a multiplication problem ending in 0. We just have 3 factors that we can set to 0 instead of the usual 2. So x minus 2 could be 0, or x plus 1 could be 0, or x minus 5 could be 0. And we just solve those one at a time. So x could be 2, or x could be negative 1, or x could be 5. So I'm just going to make 3 cuts to the number line instead of our 2 like before. Okay, furthest to the left we have the negative 1. In the middle we've got the 2. On the right we've got the 5. Notice I'm not super worried about scale here, just the order that they're in. So we'll try out x is negative 2, x is 0, x is 4, and x is 100. The reason I don't really care exactly what those are for this one is if we have this setup, multiplication problem or multiplication division problem with 0 on the other side, we can use a nice clean short sign number argument and not have to worry about the actual value of the numbers. So trying out the negative 2 minus 2 is a negative. Negative 2 plus 1 is a negative. Negative 2 minus 5 is a negative. And we want to know if that's less than or equal to 0. Odd number of negatives multiplied together gives us a negative. Negative less than or equal to 0 is true. So I want this part. Then I'll try out my sign number argument with 0. 0 minus 2 is a negative number. 0 plus 1 is a positive number. 0 minus 5 is a negative number, and I want to know if that's less than or equal to 0. Even number of negatives this time results in a positive. Positive numbers are not less than or equal to 0, so I'll skip that. Trying out the 4. 4 minus 2 is positive. 4 plus 1 is positive. Or minus 5, however, is negative, and we want to know if that's less than or equal to 0. We're back to an odd number of negatives, which is a negative. Negative less than or equal to 0 is true. So we'll keep that. We'll keep the stuff that the 4 was in. And again, we would have had those same 3 signs had we plugged in a 3 instead, or had we plugged in pi instead. Anything on this interval, e, 2.718, etc., etc. Same 3 signs. And finally, our 100. 100 minus 2 is positive. 100 plus 1 is positive. 100 minus 5 is positive, and I want to know if that's less than or equal to 0. All positives multiplied together give you a positive. Positive is not less than or equal to 0. As far as endpoints, if I try out the negative 1, that makes this factor a 0. 0 times anything else is 0. 0 less than or equal to 0 is true, so we'll keep that. Same with the 2. Just makes the first factor 0. 0 times anything is 0. We keep it. Same thing with the 5. So again, this time we'll have 2 intervals. So we'll keep from negative infinity. Notice that always gets a parenthesis. The reason being, there is no smallest number. If you think you found it, subtract 23 trillion from that number. If you think that number is the smallest number, subtract 10 from that number. And you could keep going forever. So we never get to infinity or negative infinity. Those will always get a parenthesis. Negative 1, however, since we were allowed to use it because of this or equals, and it does work in the original, that gets a bracket. Then we need that union symbol in the middle, and we'll keep from 2 to 5. So that covers us as far as polynomial inequalities. Next, we look at rational inequalities. We just have one other place that we have to look. We'll do just a temporary equation. Let's let 1 over x equals 0. If I tried to solve this thing, I would first try to clear the fraction, but then I get the contradictory statement that 1 is equal to 0. 1 is never equal to 0. This thing would have no solution. But that doesn't mean that all of my numbers, let's say we had a 1 over x is strictly greater than 0. That doesn't mean that no numbers will work in there, and it also doesn't mean that all numbers would work in there. Just think of your signs. If I plugged in a positive number for x, positive over a positive is a positive. Positive numbers are always greater than 0. All the positives would work for x. But if I plug in a negative, a positive divided by a negative is a negative, and a negative is never greater than 0. So not only do we have to try to solve the rationals, we also have to take one more opportunity and examine the denominators as well. What would make us break the division by 0 rule? So we set the denominator to 0 as well. So the rationals, you're going to have 2 let lines. This one, no more solving to do. So here's our 0. And we'll try maybe -1 and a +1 in the inequality. So 1 divided by -1, possibly greater than 0, negative. Greater than 0 is false. 1 divided by +1, possibly greater than 0, positive greater than 0 is true. So not only can I get cuts to the number line from things that would make the temporary equation true, with the rationals, it's also things that would make you divide by 0. Strict inequality, so we'll keep the parenthesis instead of a bracket. And our interval notation would keep from 0 to infinity. So we'll try another one out, a little bit more going on with it. We'll do x minus 6 divided by x plus 5. We'll make that, well, let's say less than or equal to 0. So first we solve the temporary equation. Let x minus 6 over x plus 5 temporarily equal 0. Clear the fraction by multiplying both sides by x plus 5. X plus 5 over itself is 1, so x minus 6 equals 0. 0 times anything is 0. Add 6 to both sides, and x is 6. This is just one of the cuts to the number line. If you see a fraction, you're going to need 2 let lines. The other let line is letting our denominator equal 0 and solving that. So -5 is also a critical number for this problem. So we'll sketch in our quick little number line here. On the left, we've got a -5. On the right, we've got a +6. So 3 intervals, 3 test points. So we'll test out x is, -10, x is 0, and x is 10. We just have a division problem here, so we can use a sign number argument again. So -10 minus 6 is a negative number. -10 plus 5 is also a negative number. We want to know, is that less than or equal to 0? Negative over negative is a positive. Positive less than or equal to 0 is false, so I don't want the left side. Trying on a 0. 0 minus 6 is negative. 0 plus 5 is positive. And we want to know if that's less than or equal to 0. Negative over positive is a negative. Negative numbers are less than or equal to 0. We do want the middle. We'll talk endpoints in a moment. Trying out the 10, we get a positive over a positive. We want to know if that's less than or equal to 0. Positive less than or equal to 0 is false. So as far as endpoints, the 6 minus 6 is 0. 0 divided by something else is 0. 0 is less than or equal to 0. We'll keep the 6, no problem. But taking a look at that -5, we have -11 divided by 0. That is undefined. So even though we have this or equals, I'm still not allowed to break the dividing by 0 rule. So that -5 is going to have a parenthesis even though we had an or equals. So our interval, -5 exclusive to +6 inclusive. All right. So we don't always compare to 0, however. We'll start a fresh page here. There we go. So we'll solve 3 over x minus 2 is strictly less than 2. So this is a rational. I see a fraction involved. I'm going to need 2 let lines. One let line replacing the inequality symbol with an equal sign. My other let line is going to take any denominator and set it equal to 0. So you're solving both of those. So that first one, nice little mini review on the chapter 7 stuff. Multiply both sides by the LCD. So 3 by 1 is 2x minus 4. So 3 is 2x minus 4. So I add 4 to both sides. So 7 is 2x, cut both sides in half, and x is 3.5. Our other one, solve a little faster than that. X is +2. So, again, 2 cuts to the number line. 2 on the left, 3.5 on the right. If you're having trouble putting a mixed number into, or I'm sorry, an improper fraction in a mixed number, just remember it's division. 2 will go into 7 3 times with 1 left over. Keep your original denominator. So we'll test out x is 0, x is 3, and x is 4. This time I don't have multiplication division compared to 0, so we'll need the actual numbers to work with. So first one, 3 divided by 0 minus 2, possibly less than 2. So 3 divided by -2, possibly less than 2, -1.5, less than 2 is true. So we'll keep it. So we shade this way, arrow on the end. We'll talk endpoints in a moment. Next up, 3 divided by 3 minus 2, possibly less than +2. 3 over 1, possibly less than 2. 3 is less than 2. That doesn't make sense, so we'll skip that section. And finally the 4. 3 divided by 4 minus 2, possibly less than 2. 3 halves, possibly less than 2. 1.5 less than 2 is true. Okay, the 2 would make us divide by 0. I can't keep it. The 3.5, if we had an or equals, it would get a bracket. Strict inequality, it's still going to get a parenthesis. Since 0 is not, or I'm sorry, 2 is not less than itself. If we plug in 3.5, 3.5 minus 2 is 1.5. 3 divided by 1.5 is 2. So then our intervals, -∞ up to but not including 2, union that up with 3.5 approaching infinity. Okay. So let me get some problems for you all to try out. So this was section 11.4. 1 through 41, every other odd should be sufficient. If you have questions, please get in touch with me. Otherwise, stay safe out there.